Okay, so here's what we got. I need you guys to turn your attention to the board over here. I'm going to pause the video, but to kind of bring this into mind. Okay. So the area in a curve from A to B of the function f of x dx. So this is the integral from A to B, or bounded from A to B of f of x dx. It means the area underneath the curve in the x-axis is actually equal to the sum. Yep. And we start with I equals. I is the rectangle number. So we always start with the very first rectangle. And we're going to go to an infinite number of rectangles. Or you could put n there. It doesn't matter. I'll show you why in a little bit. Okay. And then what we do is we take our heights, okay, and we plug them into the function. F of x sub I is the spots where we evaluate x. We plug them into the function. We get the height, and then we multiply by the width. If you remember, we've taken the width times the sum of the heights for quite a while now, haven't we? That's a formula we've been using. What they use to designate for width is delta x. Subscript. This says x sub I. It means the x values at which we evaluate the heights. So in our checkpoint problem today, we did 1.1, 1.2, 1.3, all the way up to 9.8, 9.9, and 10, right? So that's what the x sub I means. Okay, you plug those into the function or generate the heights. Now, what we want is we want this limit to go to infinity. So we have n number of rectangles. We want to go to an infinite number. Now, part of what you need to know is how to calculate a few of these pieces. You're fine with the limit sign. You're fine with sum. You're fine with I equals 1. You're fine with n. And you're fine with the function. What you don't like is delta x, and you don't like x sub I. So I'm going to show you what delta x is. Delta x is the width of each rectangle. What did we do to calculate the width of each rectangle? B minus a over n. Thank you, child. Now what we need to talk about is where we evaluate the heights. That's x sub I. And this is the confusing part for people. I want to try to make it clear. This is actually new for the notes this year because in previous years people have been unclear. Are you ready to get clear? Let's do it. If you're finding the area of 8 rectangles for the integral from 0 to 4 of x squared dx, it says we have a curve bounded from 0 to 4. It says if you want to find the area of 8 rectangles, what is the width of each rectangle? I want to do 8. 1/2. 4 minus 0 divided by 8. Is everybody good with that? We'll talk about that later. Don't worry about this part, okay? We'll tell you what that means later on. So if I'm finding the area of those 8 rectangles, at what x values do you evaluate the heights? Well, I'm going to kind of divide this up here. I've got 0, and then 1/2, and then 1, and then 3/2, and then 2, and then what? 5/2, and then 3, 7/2, and then 4. So at which spots do I evaluate the height? Right-hand sum. Right? I do those, right? Now, watch. What we did is you start at 0 and you added a width, right? That brought me to here. This is super important. Then we went 0 and we added 2 of the widths, and that brought us here. Then we started at 0 and we added 3 of the widths, and that brought us to here, right? All right, let's switch it up. Okay, bounded from 3 to 4 this time. 3 to 4 of x squared dx. 8 rectangles. What's the width? 0.125 or 1/8, right? Are we okay with that? So where do I evaluate the heights? I'm going to start at 3, and I go to 3 and 1/8, 3 and 2/8, 3 and 3/8, all the way up to 4, right? If I'm doing a right-hand sum, which of those spots do I evaluate the height? Right. So what you did is you took 3 and you added onto it one of the widths, right? And then you took 3 and you added onto it 2 of the widths, right? And you took 3 and you added on to it 3 of the widths, right? So now we have the area from 3 to 5 of x squared dx. What is going to be the area, or what is going to be the width of n rectangles? Use your formula. 5 minus 3 divided by n, or 2 over n. When you get back, we'll pick up with that piece. Go have a great lunch. Okay, you guys got it, that the width of each rectangle is 2 over n. Do you see how I came up with that? B minus a divided by n. Now let's just pick up where we left off. Kind of get your brain back here. When we wanted to evaluate the heights, we started at 3 for this one, but we went over 1 width, then 2 widths, then 3 widths, right? So if we are finding the area of n rectangles, what x values do we evaluate the height? Well, we start at what? We start at 3, and then our next spot would be 3 and 1 width, right? 3 plus 2 over n. And then the next one would be over how many widths? 2 widths, so 2 times 2 over n. And the next one will be 3 plus over how many widths? 3 widths, so on and so forth, right? So if we want to know where we evaluate the heights, we start at A. So x sub I will be equal to A, and we add widths, B minus A over n. How many widths do we add? We add I number of them, whatever rectangle we're at. We now have the pieces to be able to add up an infinite number of rectangles. A plus I times B minus A over n. Let's make it happen. Flip it over. Let us review a basic example and then get into an infinite number. We have the curve f of x equals x squared from 0 to 2. So it's going to look something like this. Right? We're going to evaluate the right-hand sum. Remember, we take the width times the sum of the heights. If we're going from 0 to 2, we have 4 rectangles. What's the width? Width is a half. Right? So we're going to go 1 half, 2 halves, 3 halves. Draw my rectangles. You can see it's an overestimation. So I take 1 half, which is my width, and I multiply it by. Where's the first spot where I evaluate my height? 1 half. I went over 1 width, right? So I take that 1 half and I do what with it? Square it, right? Plus 1 squared, plus 3 halves squared, plus 2 squared. You remember doing that, right? Okay, so we got 1 half times 1/4 plus 1 plus 9/4 plus 4. And 1/4 and 9/4 is 10/4. or 5 halves, plus 5, or 10 halves. So it'll be 15 halves. 1 half times 15 halves is equal to 15 over 4, 3.75. We've done that before, right? Okay. So let's not do 4. Let's do n and push n to infinity. What's the width of n rectangles? B minus a over n. 2 minus 0 over n will be 2 over n. That's the width of n rectangles. Everybody has to be okay with that. Is everybody all right? Okay, we want to figure out where we evaluate the heights. We started, look at this, we started at 0, right? We started at 0, and we went over a width. Our new width is not 1/2, but we went over a width. How many widths do we go over? We go over 1, then 2, then 3, then 4, then 5. And so that we use I in that place, because the summation will tell us that we start with 1 and then we go to 2, so on and so forth. So x sub I is equal to 2I over n in this situation. That's the spot that we evaluate the heights. Getting these two pieces is crucial for them being able to write the appropriate limit. Express the area as a definite integral and as the limit of a Riemann sum. So therefore, the integral from 0 to 2 of x squared dx, that means the exact area bounded underneath x squared between 0 and 2, the exact area, not approximation, we can calculate by taking the limit as n goes to infinity of the sum from I equals 1. So we start with the first rectangle, and we're going to go to n rectangles of f of x sub I. What is x sub I? 2i over n. This tells me to take x sub I, or 2i over n, and plug it into the function, into x squared. So 2i over n squared times delta x. What's delta x? 2 over n. The width. So remember, the whole idea is we take the width times the sum of the heights. It's right here, folks. Width, sum, heights. We don't know how to do this part. We do know how to do this part. It's really not that bad. There's just one small step that you probably don't remember from last year that we have to use. Let's multiply this out. We got the limit as n goes to infinity of the sum from I equals 1 to n of, can we square this and multiply those together? 2i squared times 2. 8i squared. N squared times n. Yo. You have to retake last year's class for saying that. Okay. Here's what we do. We take that limit as n goes to infinity. And this sum right here, what we're going to do is we're going to extract part of it. We're going to take out the 8 over n cubed, and we're going to write it as a sum from I equals 1 to n of just I squared. Do Do you see how I pulled out the 8 over n cubed? I'm left with this. I don't like the fact that we have I. Do we know how to take infinite limits? Did we practice that? Yeah, we did it. It was on your first semester final exam. You guys were good at it. You had no problems with it. So I'm not scared of this. But this, I don't want an I. I want N. What do we do? Okay, YouTube people, I just went to the board and I showed them all the different sums that we come up from doing our mathematical induction that we did at the end of last year. So we have the limit now as n goes to infinity of 8 over n cubed times, what do I put in the place of the summation from I equals 1 to n of I squared? N times 2n plus 1 times n plus 1 all over 6. So I replaced that with that. We know that that's the known sum. If you don't believe me, we can prove it. We'll use induction. You did it last year. Well, I just got to figure out that limit. Find the limit. Limit as n goes to infinity of, let's multiply this out. 2n times n, 2n squared times n, 2n cubed times 8, 16n cubed. The middles, I'll get 1n and 2n. 3n times n, 3n squared times 8, 24n squared. What's my last term going to be? 8n. What's the denominator? 6n cubed. Do you remember what we did in order to evaluate that limit? Yeah, take out the largest term. So we're going to take out an n cubed. What are you left with? Whether we write it in front or back doesn't matter. Either way, what happens to the n cubes? Gone. As n goes to infinity, what happens to 24 over n and 8 over n squared? What are you left with? Which is 2.6 repeating, right? Right? Is that it? Watch. We just added up the area of an infinite number of rectangles. I mean, that's unbelievable. It is awesome. And as you practice it, you will begin to see the true beauty of this thing right here. What I used to do, so this graph is here because people had such a problem with understanding that this marked the x sub 0 spot. So this spot marks I is equal to 1, meaning the first rectangle and the first x value. This would be I is equal to 2. That's the second spot. So this would be 1 width. This would be 2 widths. This would be 3 widths. And a lot of people right now, as you guys are looking at it, you still are kind of wondering, what the heck is this I equals 1? That means we're starting with the first rectangle, then second, then third, and we're going all the way up to the nth rectangle. Well, what's the nth rectangle? Well, we're pushing that all the way to infinity. So this whole piece right here that we wrote down, this thing is unbelievable. I mean, the definite integral written as the infinite limit of Riemann sums. Truly amazing that we're able to do that. And we did not come up with an approximation. Forget about right-hand sum, left-hand sum, trapezoidal sum, midpoint sum. We got the exact value, folks. 8/3. You do have to know how to do this for the test. You're going to be good at this. Now, this is the easiest problem I can come up with for you. We're going to try some more complicated problems. We're going to need Monday and Tuesday to figure that out, okay? You're going to get an assignment on Monday, but a lot of people had some questions about where these pieces came from. If you need to go back and watch a video from last year, go ahead. There might be a video on that. If there's not, there's one for previous years. But search mathematical induction, you can see how that works.